This is Lecture 7A for Calculus 2 on integration by parts. Integration is complicated by the rules of differentiation. The reason for this is that many of the integrands that we try to integrate are the result of these rules. So integration must sort of undo these rules of differentiation as well as find the primitive of isolated functions. There are two rules that require special techniques. One is composition, and you've already worked with this. Recall a composition. If f is composed with g, the derivative is f prime, the derivative of f evaluated at g, times the derivative of g. And in first semester, you learned about substitution, and substitution is used for this case. Okay. Here, we're working with the product rule. Now, if you take the derivative of the product of f and g, you end up with two terms, f times the derivative of g plus g times the derivative of f. Integration of this situation requires integration, let me get the pen, integration by parts. Let's review integration of the composition of functions. So we'll use an example here. Let's say f is sine x and g is x squared. Then f composed with g is sine of x squared. Taking the derivative of the sine of x squared gives 2x times the cosine of x squared. Now, to integrate 2x times the cosine of x squared, we'll use the substitution here. All right, u equal x squared. With this substitution, we have something we can integrate easily, cosine u du, which is sine u plus the constant of integration c. By back substituting for u as x squared, we end up with sine of x squared as we expected. That was for composition. Now we're going to look at the product. Right? And in this case, we'll end up using essentially two substitutions. Okay, so here's the situation we have. We're taking the derivative of f times g, and we end up with two terms, both of which are products. And now I'm going to apply the integral operator to both sides of this equation. So if I integrate the derivative of f times g, I end up with f times g. Okay, by the fundamental rule of calculus. On this side, I have the integral of those two terms, f times g prime plus g times f prime. I can break that up, since the integral operator is linear, I can break that up into these two terms. Right? And that's the situation that we're faced with when we have started with the product of two functions. So here's an example. Say f is x cubed and g is the sine of x. Then the derivative of the product, x cubed times sine x, gives us these two terms, x cubed times the cosine of x plus 3x squared times the sine of x. Now when I take this derivative, I'm going to apply the derivative operator to both sides. This is how we develop it. I get x cubed times the sine of x here must equal the integral of both of these terms. Okay, the problem is that we're not given all three terms. Instead, we're given one of these. We might be given this to integrate, or we might be given this, and we must evaluate it in terms of the other two. So I've written the situation in general here. The first lines here, let me get the pen. These are just, in general, what we did on the previous slides. But now, here is our last line, but let's isolate one of these integrals. Let's say we're given this one to integrate. Then the situation looks like this. The integral of f times g prime equals f times g minus the integral of g times f prime. Or, if we're given the second one to integrate, we have a situation like this. The integral of g times f prime equals, again, f times g minus that other leftover integral from before, f times g prime. Right? If this these left-hand sides are easy to integrate, then we just carry out the integration and don't think about it. But in general, what we do is we use this side to evaluate the integral on the left-hand side. And the idea is that hopefully, if we've played our cards right, this integral is easy to evaluate. I'll show you how to do that now. Well, before I show you how to do it, I'll just write out for that particular example of f being x cubed and g being the sine of x, I'll just write out that example and show you what we're dealing with. So we were to this, a couple slides ago, we were to this stage. All right, now here's what we're typically given. We're given one of the integrals on the right-hand side to evaluate, so I'll isolate it. For example, if we're given x cubed times the sine of x dx, then that is equal to f times g, which is x cubed sine x, minus the other integral. Or if we're given this one, let me get the pen. If we're given this one, I've isolated it here and written it in terms of the other two. That's the situation we're presented with. If you look at these left-hand sides, substitution isn't going to work. If it would work, you could go ahead and do it, but it isn't going to work, and that's why we use this integration by parts. Instead of writing the f and g's, integration by parts is written in this general way. The integral of u times dv equals uv minus v du. And so what we've got going here is that, let's say u is equal to f, then dv is g prime dx. All right. And then the goal in integration by parts is to identify the u and the v terms in this expression. Or you can think in terms of the f and g, but it's generally written in terms of u and v. And there are two ways to do it. You could identify one as u and the other as dv, then you have these different ways. But the trick is that you want to pick your u and v so that this integral is easy. We always want to end up with something easy, or at least something we can do. So that's the trick. And here's a rule of thumb. You pick u so that it should simplify when you differentiate it, and you pick dv so that it's easy to integrate. This is hard to talk about in words. You're going to have to see examples, and we're going to move towards that real soon.